Welcome to Selection Sathi. Today we learn C memory management, stack versus heap, malloc and free, and how to avoid common memory bugs. Memory management is what makes C both powerful and dangerous. It's a top topic for gate and systems programming interviews. Let's get started. First concept: stack versus heap memory. The stack is used for automatic allocation. Local variables and function call frames live on the stack. It follows LIFO order, last in, first out. Stack is fast but small, typically 1 to 8 megabytes. The heap is for manual allocation. You allocate with malloc and release with free. Heap is much larger but access is slower. Stack variables are automatically destroyed when the function returns. Heap variables persist until you explicitly free them. Stack overflow happens with too many recursive calls or huge local arrays. Heap fragmentation happens after many small allocate and free cycles. Second concept: malloc, calloc, realloc, and free. Malloc takes a size in bytes and returns a void pointer to the allocated block. The memory is not initialized, it contains garbage values. Calloc takes a count and element size, allocates count times size bytes, and initializes everything to 0. Realloc takes an existing pointer and a new size and resizes the block. It may move the data to a new location if needed, so always use the returned pointer. Free releases memory back to the system. The golden rule: always free what you malloc. Every malloc needs a matching free. Third concept: using sizeof for allocation. The standard pattern is int star p equals int star cast malloc of n times sizeof int. Always use sizeof instead of hard coding byte counts because sizes can vary across platforms. For example, int might be 4 bytes on one system and 2 bytes on another. Cast the void pointer returned by malloc to the correct type. Always check if malloc returns null. A null return means the allocation failed due to insufficient memory. Follow this pattern for every allocation: allocate, check for null, use the memory, then free it. Fourth concept: memory leaks and dangling pointers. A memory leak happens when you allocate memory but never free it. In long-running programs like servers, leaks accumulate and eventually crash the program. A dangling pointer is a pointer to memory that has already been freed. Dereferencing a dangling pointer is undefined behavior. It might work, crash, or corrupt data silently. Double free means calling free on the same pointer twice. This corrupts the heap data structures. Best practice: after calling free on a pointer, immediately set it to null. This way, if you accidentally dereference it, you get a clean crash instead of silent corruption. First example: dynamic array with malloc. We want to allocate an integer array of size n at runtime. We write int star ar equals int star cast malloc of n times size of int. Then we check if ar equals null, print allocation failed and exit. We fill the array using a for loop. Our bracket I equals I times 10 gives us 0, 10, 20, and so on. When we are done, we call free of ar and set ar to null. This is the complete life cycle: allocate, check, use, free, nullify. Second example: resize with realloc. We start by allocating space for 5 integers with malloc. Now we need 10 integers instead. We call realloc with the new size. Important, realloc may return a different address if it needs to move the data. So we store the result in a temporary pointer first, int star temp equals realloc offer comma 10 times size of int. If temp is not null, we update r to temp. If temp is null, the original r is still valid. The first 5 elements are preserved. The new elements 5 through 9 are uninitialized. Third example, stack frame visualization. When main is called, a stack frame is pushed with main's local variables, say int x equals 10. When main calls foo, a new frame is pushed on top with foo's locals, say int y equals 20. When foo calls bar, a third frame is pushed with bar's locals, say int z equals 30. Now bar returns, its frame is popped and z is destroyed. Then foo returns, its frame is popped and y is destroyed. We are back in main with only x. This is LIFO, last in, first out. Each function gets its own isolated stack frame. Fourth example, detect a memory leak. Here's the buggy code, void process, int star p equals malloc 100, use p, then return. The problem is there's no free before the return. Every call to process leaks 100 bytes. The fix is simple, add free of p before the return statement. To detect leaks automatically, use valgrind. Run valgrind -- leak check equals full./program. It will report exactly where every leaked byte was allocated. Essential tool for C developers. Quick tips. Tip 1. Every malloc must have a matching free. Think of them like opening and closing brackets. Tip 2. Always check if malloc returns null before using the pointer. Allocation can fail on low memory. Tip 3. After free of p, set p equals null immediately to prevent dangling pointer bugs. Tip 4. Use valgrind for automatic leak detection. It catches leaks, double freeze, and use after free. For more concept videos like this, download the Selection Sathi app. Like and subscribe. Thank you.